doing us this time. We got Hochschild cohomology and deformations.
This time. So I said that I'm going to say what does dB and d pi of Fock mean, right? And we said that this was, we need to take twisted complexes. And this was, I wrote this weird letter, right? So, sorry, of twisted complexes. So just very short, this is Karoubi completion or idempotent completion. And what does it mean? That was the last part of my talk. So this is all from last time. So let's do like a preliminary discussion at like when we assume that A is an ordinary linear graded category over the field K, and we make the following definition, which is if we have a morphism P, then we say that P is idempotent if P squares to itself, and we define, let's start this side of the board.
I think you can like get 3 boards. Maybe you can move this into the middle. Then you get a flat one.
Okay, that works.
Okay.
So I define the image of P. Sorry, that should be Y. Makes more sense. To be an object in our category with inclusion and retraction, where these are morphisms given by the following diagram. I want Rk to be the unit, and I want Kr to be P, and the retraction is R that goes from the Hom of to Z, and the inclusion morphism goes from Z to Y. Okay, so, and I define the split closure of A to be a pair BF such that B is split closed, and I'm going to say what it is in a second. B is split closed, and F from A to B is a full and faithful embedding. Can anybody see what my thing is too low? Or okay. A full and faithful embedding. Yes, sorry. Okay, so it's a full, what I'm saying, I'm defining the split closure, I'm going to say what split closure, to be a pair BF, where B is split closed, I'm going to say what it is, and F from A to B is a full and faithful embedding, such that, I bored. Such that each object in B, right, is the image of some idempotent in A, and of course split closed just means that it contains images of all idempotents. Yeah, sure.
Is idempotent a property of the objects or of the morphisms?
Well, being an idempotent is a property of the morphism. When we define the abstract image of an idempotent, think about the abstract image is an object, right? And containing all objects that are abstract images of all the idempotents is a property of the category. Does this make sense?
Jake,
Yes.
could we move this?
All right. What I say make sense?
I think so.
Okay.
So is it the same as Karodic learning?
Yeah, I mean it's the same. It's minimum the foot. Yeah. Yeah. Okay. So why am I spending all this time on like usual categories? Well, the point is like there is a definition like of the homotopy equivalent of this of this notion, which is like homotopy, idempotent, etc. But it turns out that actually this is equivalent to checking everything on the cohomology level. So here's what I want to say. I'm not going to specify what the definition is in like the infinity world because it just turns out to be equivalent, which simplifies things considerably. If we have an infinity category, then it turns out that A is split closed in this like infinity sense. It's the same thing as HF of A being split closed. And it turns out that you have the same notion. You can talk about a split closure of an infinity category, which would have a cohomologically full and faithful functor. And it turns out that being like split closure is the same thing as the cohomology level being split closure. So what I want to say is this functor, this is just taking a specific kind of split closure, a nice one. So you can just think about it as taking your category and just throwing in all the possible like summands of direct sum. You like, split all the direct sums. So this is all of it, really. So let me continue with it. Yeah.
This H0, can you remind what it is?
Yes, this is, do you remember the cohomology category that we talked about? Yeah, so H0 is the variant where we just retain the cohomology at like level 0. That's everything.
Ah.
Yeah. And this is just a specific kind of split closure, which you can really think about as, you can really check it on like the level of cohomology usual category theory. So, and the point is like when you take this to a triangulated category, it stays triangulated. So everything is fine. Now, let me start with topic of today's talk, which is Hochschild cohomology. Wait, are there any questions? Okay, so let me start. Can I delete this?
Okay, but not yet. How do you construct this? So I mean, if you have linear. Okay, so you define what it is, but you claim it also exists.
Yeah, actually what I defined is an envelope. I said that I defined what it means to be like a split closure. And then if I wanted to do it like correctly, I should say that all split closures are actually equivalent, right? That it does depend on the choice. Then I say that there is a specific construction that gives you a specific envelope. And I'm saying that like this is the same thing. I mean, there is a construction like in the level of the cohomology category, which is Kobe completion, and there is something like very similar in the infinity world, which is just like putting in like formal summands. Yeah. So okay.
You haven't actually told us how to do that. You're just saying it.
Yeah, I'm just saying because.
Fine.
Yeah, I mean, you can just think about it like intuitively as adding formal sums. Okay, let me start with like Hochschild cohomology. So I said in the beginning of like the previous talk that it's going to be a little boring. So I hope that this talk is going to be a little more like interesting. Okay, let's start with this lecture's topic, which is Hochschild cohomology. So this is fun. We have a new toy. So what is it? Well, the topic is this thing. Oh, we assume A would be continuous conventions from the previous talks. A is an A infinity category. F would usually denote the functor. The only thing that I want to add is now the field K is going to be of characteristic 0. So what's Hochschild cohomology? Well, it's kind of an awful definition, which says this. In the category of functors between A to A. This is fine, we're never going to use it. The point is there is a definition that talks about it as the derived self-ext of the diagonal bimodule or something like that, but we're only going to use a very, very nice resolution that's going to give us, I'm going to define a chain complex for this, okay? I'm just saying this to connect it if you've seen Hochschild cohomology in associative algebras that looks like X groups. So, H0 of Hom of in the functor category between the identity to itself. The functor category introduced in the previous talk.
The question of why H0?
Derived. I mean,
I understand. You want to be some graded object, cohomology.
Hom is graded.
I see.
Yeah. So I didn't put this definition to scare you. This is an abstract definition. We're gonna turn it into something really, really concrete and super nice. So what does it do? Well, it classifies deformations.
But one thing we see from this definition is that this is an algebra.
Yes, I'm going to say that. This is easier to see from this definition. Why is it awesome? Well, it has, so good mathematical objects should have two properties, right? They should be teaching us about interesting problems, and they should be very accessible. So this has both of these properties. It tells us something really interesting about deformations, and it has a lot of structure. What does it mean? It's simultaneously a commutative graded algebra, and at the same time it has a shifted Lie algebra structure, and both these structures are actually compatible in a way that we're not going to mention, which is it makes it into a Gerson algebra. Now we're just going to talk about these two structures separately. So it has a ton of structure, a ton of algebra, and it teaches us something important. Okay, and the other two things that I get through is two important applications for next talk, which are going to be classifying A infinity structures with a fixed cohomology. Okay, and the next thing is HKR.
What is next? I didn't see it.
Hochschild Rosenberg. Yeah. Okay. All right. So this is our plan, and I'm going to start with coalgebras. So let me just say that this is a good re-entry point. If somebody missed the previous talks or didn't understand them, I'm basically going to review some of the previous material, but from a new perspective, kind of, which is coalgebras. So let me just say that, well, if we want to define an algebra, just a normal algebra without reference elements, we're going to say that a graded unital algebra well, it really has a multiplication map, and it has a unit, and they satisfy M. This is the associativity equation. Sorry, I did this correctly. Yeah. And this is the unit equation. So a coalgebra is just obtained by inverting all the arrows, which means, can I write it? Can I erase this? Yeah. So, definition. So, a coalgebra, which is co-unital and has a coproduct, is the following data. It's a graded K vector space, and it has linear maps like this. This is the coproduct, and this is the co-unit, and they satisfy the following diagram. And this. So, okay, this is the co-unit axiom. And this is the co-associativity. Okay. So far, yeah.
Is there C at the level 0?
No, this is a graded vector space, and this is like a map of.
I'm saying, I can't read the board. I don't know if it's.
This is C. This is.
This is the whole thing.
Yeah, this is the whole thing. Yeah, definitely. It's exactly the same as in algebra. Just invert all the arrows.
So if I draw one and two here as a diagram, it would be the same.
Yeah, just arrows inverted. That's everything there is to it. So, okay, until now, nothing happened. Nothing exciting. Okay, let me make another standard definition.
Let me just hey, Mark, when people come to coalgebras, they always question why not to take a dual space and to work with algebras. And the reason is, in many cases, coalgebras have countable dimension, so some degree of reasonable dual space is completely unreasonable.
Yeah. I also heard Paul mention that in the beginning of coalgebras. Yeah. But you can't. Thank you. Okay. So let's make the following definition, which is another standard definition. A morphism F from C to C prime of coalgebras where I should probably write is a linear map of graded vector spaces. Yeah, write it more clearly? Sure. Yeah, sorry. This morphism F from these two coalgebras is exactly what you think. It's a linear map of graded vector spaces. And it satisfies following axiom. It commutes with the coproduct. Okay, so yes, and if there is, yeah, okay. So one example of a coproduct is, okay, you have the divided powers coalgebra, which just means that this is polynomials in one variable. We act on this monomial by splitting it in all possible ways. And of course, the co-unit looks like this. Okay, now for a principal actor here, which is the bar complex. Okay. So, bar construction. Okay. So, let A be a graded K vector space. The bar construction is K, A1, A tensor A, 2, etc. The coproduct splits this in all possible ways. We see how it acts on a homogeneous element. Takes this into the sum of all possible ways to break it. And it has a co-unit, which is just projection into K. Okay.
So if A is one-dimensional space in degree -1, then of the previous construction.
Yes. Oh, yes.
So I'm trying to understand this T.
Yeah.
So is it like it's T of A shifted by 1? It's like a notation, or is it functor?
It's taking like its tensor powers, right? I mean, you take A1, yeah, and
okay.
yeah, it just. Okay, so now a derivation, a co-derivation. Yes, okay. So a degree D co-derivation is a linear map such that it satisfies the co-Leibniz rule, which again is just obtained by basically inverting the arrows in Leibniz. And the space of co-derivations is co-derivation C. That's our notation. Okay. Now a DG coalgebra a DG coalgebra is a coalgebra with a degree 1 derivation such that it is also a differential. And of course, a morphism of coalgebras is required to commute with the differential. We should write it down. A morphism of DG coalgebras commutes with a differential. Okay. So, sorry. Okay. So if you recall, we basically had simple interpretation of everything in A infinity in terms of this bar construction, right? We had a dictionary. And the dictionary was what's called an A infinity structure and what's called an A infinity homomorphism are basically the same as having a differential D. This is in the level of the bar. This is on the category A. And this is on the level of the bar construction. So this is just a differential D that such that the level 0, D restricted to K is 0. An infinity homomorphism is just a morphism of DG coalgebras. And now we have this new object, which is the entire space of coderivations. And the question is, what should be put here? And the answer is just the Hochschild cochain complex. It's literally that. So let me define. I'm going to say that if I take coderivations,
Coderivations, if it just dualize, so if it's finite dimensional, it will be just derivations of the corresponding algebra. Now, derivations constitute Lie algebra and not commutative algebra.
yes.
So I have to explain.
Why is that? Why does that turn out to be like a commutative?
Commutative algebra and not Lie algebra.
Well, it's also a DGLE algebra, right?
Okay.
Yeah, but if you're, where does the product comes from?
Yes.
Well, I'm just gonna say that it comes from the Oneda product comes from like a long computation, but there is an actual argument that has to do with there are two different kinds of products here. One the tensor product, and the other the Oneda product.
Okay.
And the point is like there is an Ekman-Hilton, yeah. But I'm just gonna say that it comes from computation because you need to say bimodules. Okay. So coderivations at -1. We just need to rewrite this, okay? This is what we're going to call the Hochschild chain complex, and the homology of this, which is, and this is the homology of this with respect to a differential is actually going to be called the Hochschild cohomology. Okay.
Why do you have a differential?
Wait. Okay. I'm going to introduce the Gerson-Haber bracket and say how like an infinity structure gives you a differential. Just, yeah. I'm going to do all that. So.
So there you mean the infinity functor, or instead of homomorphism?
Well, yes, but I mean, yes, but an infinity homomorphism is like an infinity factor. Yeah, for a
But you're saying in category.
yeah, but yeah, but throughout this talk, I should thank you. I should probably say that I'm pretty much restricting to just infinity algebras for convenience sake, which is just, well, just the same as an infinity category with one object. Thank you. So just to make sure, the general like strategy makes sense. Like, I mean, I'm saying that this is like a really, really simple object. The coderivations of the bar complex -1, that's all there is to it. That's the Hochschild like cochain space.
Why coderivations are differential?
Why coderivations have differential? Yeah. Okay, I'm going to get to that. Okay. So, okay. Did everything that I say so far make sense to everybody?
What is the right-hand side and the bottom line?
Coderivations shifted by -1.
So the right
Co-derivations. Yeah.
Maybe if you could just do a recap of the strategy, what are we trying to do?
Okay, our strategy is this. We had a bunch of objects. We had a dictionary that translates from infinity algebras to coalgebras, to this by this bar construction. So we already know what an infinity structure is, an infinity functor is. Now I'm saying we have this very, very natural object in coalgebras that we want to focus on, which is the space of coderivations. So what I'm saying, all we need to do is rewrite this and reinterpret it in the infinity world. And this is going to be all our technique. And we're going to see that this has a bunch of algebraic structures. And this is going to be basically all the things that we talked about, the algebra and etc. Okay, so let me say that the Hochschild cochain space is defined to be the Homs defined to be this. Yes, just a second, I finished writing. The Hochschild cochain space is defined to be the Homs from the bar construction to A, which is defined to be the product over all orders of D of Homs from A tensor D to A degree minus D. And I claim the following thing. The coderivations are exactly the same thing. There is a correspondence. And it goes like this. So on one side, if I give you a coderivation, you can just compose it with projection to the A1 component, right? And this is going to give you your maps. It is going to give you, you take a coderivation, you compose it like projection to the first summand, and you get this. You get something here. Okay. And the other direction, if I give you something that sits in this space, well, you can just map it to the coderivation that acts in the following way. Order G, sum over all ig plus minus ad tensor gamma g, ai plus g, ai plus 1, tensor a1, and just extend by linearity. Okay. So this is the first thing. Second thing.
About the Hochschild cochain space.
Yeah.
This is the definition of Hochschild cochain space, or this is
Yeah, this is the definition of the Hochschild cochain space, and I'm saying that this turns out exactly what it to be, this familiar object, which is just the shifted coderivations. Okay. Now, make the following definition. If we are being given two cochains, then we have a circle product which is basically all the ways of sticking one thing into the other thing. In formulas, that means... What is this saying? Which one?
Gamma thing?
Gamma is a coderivation, okay. And I'm saying compose it with a projection to A1. Yeah. And then you get a bunch of elements. Right? This is a graded space, right? You have, okay. And you get a bunch of elements here.
All right. Okay.
Yeah. Does this make sense?
Yeah.
Okay, good.
What is it? Gamma L is a map from A to the L, or A to the, I'm not sure if it's D or an L. But
A tensor D to A, shifted by minus D. Yeah. Okay. So the circle product does the following thing. You stick in
I cannot see
this part
this. This I can see. But below.
below. Okay, so let me open it. Yeah. Okay, so can I delete this? Yeah. Okay. So, okay, the circle product is going to be the following thing. Well, it's all the ways of sticking one thing into the other thing. And of course, this does not have a meaning in terms of co-derivations, but in terms of the Hochschild cochain space, that it makes sense. It's not commutative, it's not associative, but you can do it. Okay?
Can you read what
You take alpha circle beta. The diff component means you take all the ways of sticking one of these maps into the other map and just sum over them. That's all. That's all I did. Okay. And this is not commutative, not associative. Does make sense in sense of derivations, but I just defined something. Okay. So shift first quickly to, okay, let's talk about why is this a DG algebra. This is the Lie bracket, known as the Gerson bracket. Going to be part 2. Okay, so let's start with the following proposition, which is if we are being given a graded coalgebra, then if we have two co-derivations, we can define the difference of this circle product. So this is not a co-derivation. This is not a co-derivation, but the difference is a co-derivation. Okay, and so this is the first statement. This is actually gives you a co-derivation. Second statement, this bracket makes the space of co-derivations into a graded Lie algebra. Second statement.
This is just saying an analogy of, take the commutator of two derivations.
Exactly.
Derivation.
Yeah. This is not very. This. Yeah. So next thing is, let's say that we have a graded coalgebra, and we've chosen some kind of a mu, which is a degree 1 co-derivation, such that it satisfies u bracket mu 0. Well, now we can define a differential by using this bracket, and this makes co-derivations into a DGLE algebra. Okay. So now we have a DGLE algebra, and we want to deform something, right? Because we have this.
You said that this bracket makes it into a Lie algebra. So isn't the bracket of everything with itself should be 0? It's a Lie algebra.
The bracket of everything. No, it's a graded. It depends on the grading, right? Yeah.
Super algebra.
Yeah. Super. Okay, so now we have this vague DGLA philosophy, which I'm not going to say too much about, but we know that in characteristic 0, like deformation problems are controlled by DGLA. So we have a DGLA. It makes us want to deform something, like be violent. Okay. Now let's recall, well, how convenient. We said that a non-unital A-infinity structure, well, that it was just the same as, right, having something that does this. Okay. That was from the previous time, the bar construction interpretation. Note that this is exactly the infinity equations, because that means stick mu a into mu a, right? What does this bracket mean? Stick one into the other. You open this up, you see this is the infinity equations. Okay, so this is very convenient. That tells us that if we have an infinity structure, then this space becomes a DGLE algebra. Okay, so let's define a first order deformation. Concretely, well, first a deformation of the infinity algebra. We start.
What exactly are you defining this definition?
I'm defining a first order deformation of an infinity algebra.
Oh, and did that prove the previous one?
That's, I should say, it's probably recollection. This is recall the definition of an A-infinity structure in this language, right? I mean, yeah. Okay, so first order deformation of the A-infinity algebra A is a K epsilon linear, where K epsilon, K epsilon is just take your field, add epsilon, quotient epsilon squared, is a K epsilon linear infinity structure on A epsilon, which is just the extension, right? And it reduces to A if we set epsilon to 0. Okay, great. Let's do it like more concretely and less abstractly. So more concretely, what's happening is we introduce some kind of a formal variable called epsilon, and we just modified our previous infinity structure by some small contribution, which is this. This looks like mu a plus something times epsilon beta, where beta is in CC2 and beta 0, the 0 component is 0. Okay, so we want this deformation, right? We took our A-infinity structure. A-infinity structure, you can just think about it as some kind of something in a cochain space, right? And we decided to add to it another cochain. So we want this to also be an A-infinity structure, right? So let's write down the equation. Can you do this? Yes? Okay, so the equation to being an A-infinity structure. Wait, the room has gone quiet. Is what I'm doing like, is it clear? Please ask if like it's unclear.
Could you repeat the
You
last
consider
construction?
is usually considered deformation is not deforming the space, but deforming the structure.
Yeah, you can think about it. We have a fixed like a vector space, and we're deforming the differential on it. Yeah, and okay.
And the idea is you just write out like a power series expansion of a deformation, but you say that, well, it only has to be consistent up to order 2.
Yeah.
So epsilon squared is equal to 0.
Yeah, it's
So you just have like some differential which depends on a variable, and then you just ignore all contributions of order higher than 1.
yes. So this is this, and let's open this up. Well, let's see. We just get half of this and this, right? Plus half of epsilon this and this, plus half epsilon this and this plus half epsilon squared of something. So this cancels, and we want this to be 0, right? So what's the conclusion? Well, for this to be an infinity structure, this is equivalent, the same statement, as saying that mu a b 0, but that's just what we wrote as d of b, where that was the Hochschild differential. So if we add, we do this small deformation to the infinity structure, then like the infinity structures are all given by b's that are cocycles. So this is the good thing. We know that like
Don't these cancel out anyway?
What do you mean? This?
If this is a lead bracket, then you switch this
Graded. I know, it's annoying. Okay. So, okay. So similarly, let's say that some of the deformation might be isomorphic. When we say the notion of being isomorphic means that you have some kind of a map of coalgebras which looks like identity plus epsilon f. That makes g of mu a epsilon equal mu a epsilon g. Then we'll say that mu a epsilon and mu a epsilon hat are isomorphic. I'm saying that up to first order you can't do anything, right? G is the identity plus epsilon times f that commutes these two.
This is a condition or
This is a definition of what it means for like to define an isomorphism between these like two deformations. I'm saying that like now we know that all deformations, space of deformation is the same thing as Hochschild cocycles. Now not some of the deformation are going to give us exactly the same thing, right? So we want to like quotient out by all those that are look the same. So I'm saying that there is a natural definition, which is, you know, you don't change what happens like when you set epsilon to 0, and you only like have this up to order like 2. And when you open this,
maybe just have the domain of G. Just maybe write what G maps to what.
What G maps?
A to A or something like that.
Identity plus something.
I denoted it, right? A epsilon, right? That was A tensor like K epsilon. Yeah, so A epsilon to A epsilon hat. Right?
Epsilon.
isn't this an A infinity homomorphism?
Yeah, this is 2 A infinity algebras, right?
Yeah, so G has components from A epsilon tensor all powers to A epsilon.
Yeah, okay, you're right. Yeah, I should probably write this as from TA epsilon 1, right? As a map of coalgebras. Okay, to TA epsilon hat 1. Okay, so this is a map of coalgebras that commute with the differential.
Wait a second. What's epsilon hat?
What's epsilon hat?
Does that make
That's the other that's another deformation.
What you're writing now doesn't make sense.
Okay.
Because identity can only map something into itself. There's no way it can map one object to another object.
But they're the same vector. They're the same vector space.
Same vector space.
Yes, but we have different differential.
So it's better you know this vector space in a way that's dependent on itself. No epsilon epsilon.
Okay,
There's
so
one vector space.
okay, there's one vector space and it commutes the coalgebra structures on this vector space. Okay, so let me denote this underlying vector space by V. And this is just the bar construction. It maps from V to V and it commutes their structures as coalgebras with the co-differential, the differential.
Mu A plus epsilon beta with mu A plus epsilon beta.
I'm missing what?
On the left,
Yes.
You have the
Mu.
infinity structure mu a plus epsilon beta.
Yes.
On the right, you have the mu a plus epsilon beta prime.
Yes. Okay. You want me to? Okay. This would. Okay. This is okay. This is a notation thing. Okay. Fine. Fine. This is deformation 1. Mu a epsilon is this. Mu epsilon bar is mu a plus another epsilon times b prime. Yeah. Okay. And all I'm saying is, when do these two deformations give you the same thing? Okay.
Just write what V is now that you've written. I mean, just it remains in the words.
B and b prime are both like in CC. Okay. Yeah. V is T A 1.
No, tensor. C of epsilon.
Tensor K epsilon. Yes. Okay. Okay. And of course, this, I guess, for sake of neutrality, should be considered without like the, just as the underlying vector space. Okay. So all I'm saying is, let me just, is CC2 gives you the space of deformations, and HH2 gives you the space of deformations up to isomorphism. Okay. Let me say something about classifying like infinity structures. Can I delete this?
I don't understand why this is a co-boundary. Oh, boundary.
Why is that a coboundary?
Yeah.
Yeah, okay. Well, I don't want to delete this. Okay, so you write this equals this, and you expand it out. And in the end, you're going to get the b minus b prime. It should be a coboundary. Should be the Hochschild differential of f. You just open this like and cancel things out. Okay. Okay. So let me say something about, okay. You know, at first I should probably mention, like you said, the unit product structure, just in a word. You know what? No. How much can I go over time?
Well, maybe, I mean, we shouldn't go like a half an hour over time.
Okay.
So, but
25
this
minutes.
is kind of, maybe we should sort of stop on time and maybe, if necessary, just an extra lecture at the end or something, or maybe some of this will go to next talk. I mean,
Okay.
just state a theorem. I mean, maybe 5 minutes.
Okay. Classification of infinity structures, you know, with a fixed cohomology. So let me just say a big picture of what's going on. Well, we have this nice like picture thing. We were going to have UA. I'm going to define it in a second. That would be the space of all infinity structures with a fixed cohomology. And we're going to have a C action that acts here that contracts everything. And we're going to have some kind of a group of formal diffeomorphisms. And the C action is going to descend to the quotient. And in here, we're going to have a canonical base point. And this base point is going to be, this is going to be the moduli space of A infinity structures on a fixed vector space with some given cohomology. And the point is this. You think about this space. You think it's a space of all infinity structure. You think about all the quasi-isomorphisms between them, which is this action of this group. You think about the quotient. In this quotient, there is a canonical base point. This base point is things that are quasi-isomorphic to the cohomology as a graded algebra. And the point is like there's a contracting C action.
So the cohomology has an infinity structure on it?
I mean, the cohomology is a graded algebra, and therefore like A infinity, right?
Trivial.
Trivial A infinity structure. An algebra is in particular an A infinity algebra. And the point is like, is going to be a contracting C action here. So in this situation, this is an observation by Kadishvili. The tangent to this point probably tells you a lot about the moduli space itself. And the tangent in this point is actually the Hochschild cohomology because that controls deformations. So onward with like definitions.
So it's Hochschild. Since you take only one point, so it's Hochschild cohomology of this cohomology algebra.
Yes, the Hochschild cohomology of this like cohomology algebra. Let's say the cohomology algebra, I'll try to denote it by A, which is like boldface, and all A infinity structures going to be A hat. Yeah, thank you. Okay, so G of A. That's curly G of A. The text engine is not that good on my hand. Yes, I'm going to define that.
What is the fixed point?
The fixed point is all like formal structures, which means they're all infinity structures that are quasi-isomorphic to their cohomology algebras as a graded algebra.
To their cohomology algebra?
Yeah, I mean, this is the modular space of all infinity structure with a fixed cohomology, right? And I'm saying that this is everything that's like quasi-isomorphic. To that, exactly. Okay. So we start with A, which is some kind of a graded algebra. And I'm going to denote the multiplication. M is going to be the multiplication map. And this is mu of A is space of A infinity structures on A such that mu1 is 0 and mu2 is -1 to the A1 multiplication of A2 A1. Okay, so that just means that they have the same like cohomology. G of A is going to be the space of all G's that go from 1A hat A. This is an A infinity homomorphism. And between A and A hat, this is an A infinity homomorphism between two different A infinity structures. Like yeah, G1 is the identity. These are called the formal diffeomorphism. So like kind of a power series that starts with 1.
What is A hat? What do you start with? Do you start with the infinity algebra or you start with its cohomology algebra?
I'm starting with a cohomology algebra and I'm considering.
So I don't know what's A hat. I don't know what is
A hat.
You start with A.
Yes.
So what is A hat?
So there's a straight A, which is the cohomology algebra, and there's a curly A, which is an A infinity algebra, and there's a curly A tab, which is another cohomology, which is another infinity algebra.
Yeah. What's?
With fixed cohomology.
Yes.
It means we started with some algebra.
Yes.
This algebra denoted by A.
Yes.
No A hat yet. We could define all possible A infinity structures.
Yes.
With that cohomology. No particular A infinity. So you're asking what is A hat?
It's font. There's this curly A, which is the A infinity deformation of straight A.
Yeah.
And curly A hat is another A infinity deformation of straight A.
So J of A depends on the choice of the hat of node. That's a notation if that makes sense.
I'm just
The left side
yes.
depends only on A.
Yes.
A doesn't define uniquely A hat. So I don't know what's it.
Wait. Okay. So I'm just trying. You mean this is A hat, A prime, right? That's what you call. Okay. These two things, A and A prime.
So the left side depends on A or also on A prime? What is the left side?
Left side. This
Depends only on A.
yes.
Then no A prime. I don't know what's A prime.
A and A prime are two elements inside U of A.
The right side depends on two elements, A and A prime. The left depends only on A. Notation I
Maybe you
don't
can
understand.
change letters and
No, I think that you consider all A infinity
Yes.
structures A,
Yes.
squiggly A and squiggly A prime.
Yeah.
So they're not fixed.
Maybe
I
on
mean,
the
not
right
fixed.
A prime and UA. On the right is
On
the
the right.
vertical bar.
Right.
You want
Next to G1 equals directly.
It's under
A
there.
squiggly and squiggly A prime are inside U of A.
yeah, I would that. Ah, you're saying right in here. Okay.
You run over all A squiggly
Okay.
and A squiggly prime.
Okay, A and A squiggly prime are in U of A.
Okay,
Okay? Does this make sense now?
fine.
Hmm?
So you choose, on the right side, you choose two deformations and consider maps.
Yes, exactly. Yeah. Okay. So, and we have
So it doesn't have any
This is what-
structure. It's not a group.
This is not a group. What you wrote.
What you write is not a group.
what I wrote is not a group.
I think what you want to take is all sets of maps from straight A tensor S to A.
Yeah, okay. Yes, I want to take. Okay, G denotes like. Is that G denotes like a this is an infinity homomorphism? Yes.
Right,
Okay.
something that could be an A infinity homomorphism. And then you want to define an action of this thing on A infinity structures.
Okay. Fine. Okay. Let me rewrite this in a way that like be more clear. Okay.
So is it just G of A, all automorphisms of A considered as A infinity algebra?
I mean,
Just one second. One would way, A is an algebra. You can consider it as an infinity algebra. And now we can consider automorphism of A as an infinity algebra. This makes sense. This is a group. I don't see any other group.
trying to understand problem.
I think we should stop.
Wait. 5. Can I take like 5 minutes? Just 5 minutes.
The thing is that it may be worthwhile. Are you speaking? And maybe like we can sort of append something to the beginning of next talk, or either Nick will say something or you will say something. I mean, but
Okay.
it's difficult to concentrate after an hour.
Okay.
So somehow, maybe we should.
Okay, fine.
So, are there any questions at this point?
Yeah. So let me start. Okay, I'll start with
Is
that.
it obvious what the C action is, or
It's-
is that obvious?
It's scaling the n. Okay, it's the action of epsilon on a mu d just scales its components by epsilon d minus 2. Okay.
So, yeah, let's have a break now for. It's supposed to be like 15 minutes. Maybe we'll take
Yeah,
a
sure.
10-minute break. So it's going to be starting at
Yeah, sure.
10:15.
Okay, fine.
Okay, so.
Maybe we should